first thing, let's focus on here. I want to compare the first best quantity and the second best quantity. Okay? Even though I did not explicitly solve the first best problem with complete information for continuous type, I hope you may verify it by yourself or convince yourself that the first best quantity should satisfy this equality. Okay? This equality. This is true for 2 type, n type, and the continuous type. This defines the efficient quantity. And this, the second equation, which we have just obtained from the previous video, defines the second best quantity. Now I want to ask which one is larger. I mean quantities, which one is larger. Okay? Here, theta is here. Theta here is minus something. And you may see for every capital F, small f, this term is positive. Right? This term is positive for every theta. And that means the whole thing here, the coefficient here is smaller. Okay? And this term is larger. The right hand side is the same. What does that mean? That means this part must be larger. I mean larger than this part. Okay? So we know V prime is a decreasing function. Okay? V is something like this, and the slope is decreasing. V prime is a decreasing function. So if your V prime of Q star is greater than your V prime of Q first best, that must means your Q star is less than your Q first best. Okay? So we have this conclusion. Q star of theta is less than Q first best of theta, unless your theta is the highest type. Why? When theta is the highest type, this ratio becomes 0, and you have efficiency. So this is exactly our efficiency at top condition. And now you know more. It's not just saying that efficiency at top. It also says inefficiency for all other types. Okay? Only top has efficiency. That's the first conclusion. Also, we have no rent at the bottom, and this has been done in the previous video. Okay? And also, you know it's not more than it's actually more than this. It says positive rent for all other types. Okay? Finally, we want to see whether we still have monotonicity. And actually, this is something to verify, right? According to our optimal solution, we need to verify it satisfies monotonicity. Otherwise, it cannot be optimal because we have just removed the monotonicity. Okay? So let's see this. How do we see this? Let's focus on our equation here. Let's focus on how Q is defined. Here, in order to show this, I need to have an assumption. So let's do this assumption. The hazard rate of our type theta, okay, defined like this, which is a ratio of your PDF and your 1 minus your CDF. We assume the hazard rate is increasing in theta. Okay, what does this mean? Somehow, if you have learned taken a probability course or something similar, you know what's hazard rate. But if you do not know, yeah, that's fine. Just treat it as this definition. And why do we say this is increasing? It's because this condition is satisfied by most of the well-known continuous distributions. For example, normal distribution, uniform distribution, exponential distribution, and most other distributions that you may name it. Okay, so this assumption, technically we need it, but it's a mild assumption because it is satisfied by most regular random variables. Okay, so if we have this, what may we say here? Suppose theta becomes higher. We know the first term is going to become higher. This term is the reciprocal of this hazard rate must become smaller. But if you minus that, it's going to become higher. Okay? So eventually the ratio becomes higher. When theta becomes higher, that means this part must become smaller. If this becomes smaller, that means quantity becomes higher. Right? Higher in theta. So that means monotonicity is true, is verified, or is satisfied. Our optimal quantity, if you take differentiation with respect to theta, this is non-negative. Okay? That's good. So we have all those major findings or implications still valid under continuous type problems. The last thing I want to tell you is about local IC. So as you still remember, we removed the local IC before we complete our solution process. Now we need to somehow verify that local IC is satisfied. Okay? So we first need to write down local IC. Local IC is something like this. Okay? How may we show this is satisfied? Let's go back to how may we express t as a function of q. We know t is determined in this way. Okay? T as a function of q. Now let's see, if we take a first order derivative of t with respect to theta, what's going to happen? Okay, here theta is a variable. So if I do this, I'm going to get this thing, right? There must be some. Oh, no. Wait a moment. Oh, I made something wrong. I'm so sorry. Okay, let's go back and do that again. As you know, this term is not t. This is w. Okay. So t is actually v of q of theta times theta minus that weird function. T is this guy. Okay, now if I do a differentiation of t, yeah, we're almost there. For theta, it becomes nothing. Or theta is there, but we differentiate the second term. Or for the last term, we have done so is v of q of theta. If we do this, we can see the first term and last term cancel each other. And what's this? V prime of theta is blah blah blah. Okay? This is exactly the left-hand side of your local IC constraint. So that means as long as we give transfer payments according to the quantity in this way, which we did in our optimal menu, if we do so, local IC must be satisfied. Yeah. So we're good. Okay. So this actually tells us something more. If you have a problem, you may do what we did: relax IC constraints, and then use the envelope theorem to get the transfer payments like this, and then find the optimal quantity. That's one way. Or you remove all those IC constraints, and then you, replace IC constraints by monotonicity and the local IC. And then you start from local IC, do an integration to get this. Okay? You may show that if you do an integration, you're going to get this. And then What's more, from here you may again find the optimal solution. You don't really need to use the envelope theorem. But after this, what do you need to do? You need to somehow verify monotonicity, right? So eventually everything is equivalent. You may use envelope theorem, or you may go from local IC to this equation. Yeah, both are somehow identical. Okay, so I would say when people are writing papers, the more standard way is to use envelope theorem, and then after they can derive the optimal menu, they can verify those IC constraints or local IC constraints they need. Yeah, that's the typical way. But anyway, you know that's equivalent. Okay, so with that, we have finished the lecture for this week. We solved this continuous type problem, show that all those insights are the same, and something regarding how to solve this problem. Yeah, so yeah, that's all. Thank you.